Okay, we first give some overview of optimization. So what we're trying to do in this class is to solve problems like this. Say we're really trying to solve a minimization problem in optimization. And what that means is we are given this kind of function, f of x, and then we try to find the minimizer of it. So this f is a function from omega to the set of real numbers. This omega is a subset of the n-dimensional Euclidean space. This n is the number of variables in X, so it's also the dimension of X. So in practice, our n can be very large, but let's just think about what you probably have seen before, that if n is just equal to 1, then this function f is just be something like this. This is x, and your function f looks like this. Let me draw this one like this. So if this is your fx, and the question right now is, where is the minimizer? So how to find this x that minimizes this f? So what we're interested in is probably this point here. Want to see where it is minimized. So this is the one-dimensional case, in which case you know that you can find the minimizer by taking the derivative of f and set it to 0, and then solve for the x. So when you solve for this x, you get the so-called critical points, where at this critical points you will have derivative equal to 0, and in this picture above, you see that this point right here has a derivative equal to 0 because the tangent line has a slope 0, and also here you have a derivative equal to 0. There, right? So you actually, when you solve the f derivative of fx equal to 0, you get these 4 points, and they're all the critical points, and the minimizer will be one of them. That's what you see in calculus, right? This is the simplest case where the function f is just a mapping from the set of real numbers to the set of real numbers, where this n is just equal to 1. But in practice, we have lots of complications, as I'm going to talk about later. Okay, so keep this in mind. Let's fix some terminology. First of all, this f will be called the objective function. This is the formal name for this f. Sometimes it's also called the cost function. And in some cases, it's also called the loss function. Just to be interpreted that the minimization is, or the optimization problem is try to minimize the loss or try to minimize the cost. So this f, this is the function f. Now remember that it's a mapping from Rn, or a subset of Rn, to R. So it gives you, take any vector, n-dimensional vector x, and it gives you a scalar, a number. And this f is the objective function. And then this right here tells us where you should find your minimizer. Okay, the omega tells you the set where you can find your minimizer, or actually gives you a constraint that your x has to be in this set. In the simplest case, the omega is just the Rn itself. In this case, we call this a unconstrained minimization. That means you can find wherever you want and just try to focus to minimize this f. This is the unconstrained case. It's the simplest one. In some cases, x, you will not have this omega equals to R n-dimensional Euclidean space, but it's just a subset. In this case, it's usually called a subset constraint minimization. For example, you want to find your minimizer, but you want your minimizer to be, say, in the first quadrant, where all the components of x greater than or equal to 0. So you can find a minimizer, but you don't count those that are, have negative values. Okay, and in the most general case, this omega could be specified by some other functions, like in this last case. Your omega is a set of points x, where the g of x equals to 0, and hx is less than or equal to 0. This is the constraint that are given. You could be given some other types of constraints, but these two are most common. The reason is this specifies the equality and inequality constraints. So if you have some other constraints like hx greater than or equal to 0, then you can convert it to this form by taking negative sign on both sides. So this is a pretty general, in the sense that you can usually convert other types of constraint into this form. And this kind of constraint is called functional constraint minimization. Okay. So now let's say that to form a minimization problem, we need to specify the objective function. We need to specify what is the variable we're trying to minimize over and what is the constraint set of this minimizer. Okay, so this together is called a minimization problem. So you may ask why don't we consider maximization problem? Or the reason is if you want to maximize some function, it's equivalent to minimize the negative of that function, right? So if you have this, if I'm having this maximization, I'm trying to find the maximizer of this function fx. Again, do this, and this is equivalent to minimize the negative f of x. So you just change your objective function f to negative f, and then you get a minimization problem. So as you can see that we can just focus on the minimization problem like this. So this is a standard form or a standard case that in optimization that we only consider the minimization problems. Okay. Okay, so after the introduction of the problem itself, we will be interested in some quantities for the optimization problem or minimization problem. So the first notation is called the local minimizer. So we say that the local minimizer x star is a local minimizer if there exists some epsilon such that the fx greater than or equal to fx star. So what this means is I can show you by a very simple picture. Say I have, let's just say the 1D case, and I have this function, and I have this function here. Okay, so I'm going to say that this point x star is a local minimizer in the sense that it's by definition, it takes the smallest value in its neighborhood. So for any x in its neighborhood, this bx star epsilon is the ball centered at x star with the radius epsilon. So in 1D case, this is just a small interval around this x star. So it's centered at x star with the radius epsilon. Okay, and in the high dimensional case, it will be just a ball. You can imagine in 2D case, it will be a disk. In the 3D case, it will be a sphere or a ball. In 4 or high dimensional cases, you can just imagine that will be a ball there. So what this means is that within this neighborhood or within this ball centered at x star and with the radius epsilon, there's no point that can take smaller function value than this x star does. Okay, and that is exactly the case here. So you have x star here, and you look at this neighborhood. It could be very small, but it's okay as long as there is some neighborhood there. And within this neighborhood, there's no other point that can take a function value smaller than the f of x star. Okay. Well, in this case, you will see that maybe this point is okay. It's also local minimizer as well, because although it is taking a function value larger than this, than the one on the left, but still within its neighborhood, it has the smallest function value, and that's true. In this case, both of these 2 points are local minimizers. Okay, so as long as it's taking the minimum function value within a neighborhood. It doesn't matter how small this neighborhood is. Then this point is called a local minimizer. Okay, so as you can see now that a function could have one local minimizer, could have multiple local minimizers, as long as it satisfies this definition. Okay, so in contrast to local minimizer, what is global minimizer is that, again, let's take this function as example. The global minimizer will be the smallest function value you will find. It doesn't matter where it is. It doesn't matter where the other points are. It always takes the smallest function value among all the points that you're considering within this domain omega. Okay, and in this case, this is called a global minimizer. So now this point is no longer, or this point is no longer a global minimizer, because although it's local minimizer, but it's not really taking the smallest function value among all the points, all the valid points. But this point stays as a global minimizer. So in general, we're trying to minimize some function. We're interested in global minimizer, if that's possible, if that's ever possible. And this type of minimizer is not as good as a global minimizer in general. Okay, so we will be interested in finding this rather than a local minimizer. But the problem is that in practice, it's really hard, especially in high-dimensional case. In one-dimensional case, you could just compare the function values. Say you got this point and you also got this point. They just compare their function values. So whichever has the smaller function value, whichever is better, right? But if it's high-dimensional case and there are so many minimizers there, then there will be local minimizer there. Then it will be really hard to determine which one is the global minimizer, which one is not. Okay, so that just give you a heads up that the two types of minimizers you may encounter in practice. Sometimes we may also consider strict local minimizers. So this means that within the neighborhood of x, all the other points are taking function values strictly greater than the f of x star. So we'll see that, for example, pretty similar to the previous case. If you look at this point, this will be a strict local minimizer, right? Because it seems that this point right here has the smallest one, and all the other points in the neighborhood have a larger function value. Right? Only this point itself has the smallest function value. This is in contrast to this case. Say I have this as my local minimizer. Okay, I can say this is local minimizer because within the neighborhood there's no other point taking function value less than f of x star. But it's actually lots of points in the neighborhood taking the function value equal to f of x star. So in this case, this is not a strict local minimizer, but this case is a strict local minimizer. Okay, this just tells you that if it's actually the only minimizer in its neighborhood, or it's just it's just one local minimizer among many others in its neighborhood. Okay, and since we have a strict local minimizer, define strict local minimizer, we can also define strict global minimizer, and that will be the case here. So if I have x star, then this appears to be a strict global minimizer if all other points are higher than this point, other function values are higher than this. But in this case right here, you can see that although it is probably taking the smallest function value, but it seems that there are lots of points around here are taking the same value. So in this case, we will not have a strict global minimizer. So this is strict global minimizer, but this is not. Okay, so we have local minimizer, global minimizer, strict local minimizer, strict global minimizers. And if you're trying to maximize something, or if you're looking for the maximizer, then you can define something similar, right? Just replace the minimizer by maximizers. But as we mentioned earlier, usually if you are trying to minimize a function, then what you're looking for are minimizers. Okay, so as I just mentioned earlier, that we're looking for a minimizer in omega, which is in a very high dimensional space. So the omega is in Rn, and n could be very large. So how large it is? Well, usually you would encounter something like hundreds or thousands, but in real applications, the n could be millions or even billions. So you can imagine how in such a high dimensional space, finding a minimizer could be really difficult, right? You cannot really do the one-dimensional case, take a derivative, set to zero, solve for it. It's basically impossible to do that anymore. So what people usually do is this. So I'm drawing this picture in 2D case, so you can see the picture better. So suppose this is the plane, and x is just say in this case, omega is just two-dimensional Euclidean space, and you're looking for a function defined. You have a function defined on this omega, which is the plane here, and then the function value will be the third direction, which is popping out of the screen, right? And so you're looking for a point on this plane such that the function value is minimized there. Okay, so say if I draw a so-called level set of the function, so what I mean is, I guess you all took a look of some maps. If you're trying to do hiking or you try to climb up some hills, then you know that some maps are labeled with the level sets, tells you the altitude of the locations. So the level set is basically similar like that. Say for example, you have this mountain here. So this is the map, and you have this mountain here, and this is the peak of this mountain, and they will show you some contours like this. For example, this tells you that you're at, for example, 0 feet, and then this maybe tells you this is 100 feet, and then the next one maybe is giving you this 200 feet, so on and so forth, and this tallest point is the peak. Okay, and similarly we can do this thing for a function. So let's say that I have a function. This is a level set which tells you that the function will be taking value, say 10 here, and then you have this one here, and the function will take value 5, and then this may be taking value 2, and at the center there will be the smallest value, say the function value is equal to 1 there. That's the minimum value. Okay, and now imagine that you're given this function, but you don't really know where this point is. You just know that for every point you can evaluate the function, the value of the function, and maybe you can evaluate the gradient of that function. But the point is that we're looking for this minimizer here, but at the beginning you have no idea where it is. So what you would do is you're going to start with some initial guess. Say I'm going to start here, and then I will try to go towards this minimizer. So what I'm going to do is say I go this direction, right? And then I found a new point. I see, okay, I'm going down, and it's getting close. It should be getting closer to the minimizer. Then I'll go further, and then further. So it's like this is the minimizer, like a star, and you start with some initial guess, and you're going to go towards this direction. You have no idea where this X star is. You just go that direction, and then once you reach to the new point, you're going to find the next direction you're going to go. So maybe this direction, and then this direction. Eventually, you go to the minimizer. So the direction is very important. So to determine the direction, we first want this direction to be feasible. What do we mean by that is, say I have a constraint set. Say this is the omega. Again, it's in 2D case. I can only find my minimizer within this set. So now I start from this point, say. This is my x0. So I start with the initial guess and say this is the minimizer x star. Okay, I'm going to go from x0 to to the next point. Hopefully it's getting better. Now you may wonder which direction I should go. So I can go this direction, this direction, this direction, or this direction, this direction. So as you can see, the 3 directions on the right, at least it will not make you outside of this. It will not make the next point outside. If you're going these 2 directions on the left, then the next step will stop. It will be outside of this omega. So these 2 directions will not be feasible because once you move along those 2 directions, the new point will not be inside omega anymore. These 3 directions will be fine. Okay, so this is the intuitive understanding of feasible directions. Okay, so now let's go back and see formally what this feasible directions is. Okay, so we call this D a feasible direction. If starting from this x, if you are not walking too far away, you just go along the direction D, but you're not going too far, then this x plus alpha d is still inside omega. Then this D is called the feasible direction. So that is the case I drew earlier. So if this is omega, and this is your x, and then it doesn't matter which direction you go, as long as you are not going too far, right? For example, if you go too far, then you're still outside. But as long as you're not going too far, there exists some epsilon, so that as long as you're not walking further outside of epsilon, your step is not larger than epsilon, will be still inside omega. So that's why in this case you will call it the feasible direction. So that means these 3 are all feasible directions. But the 2 I showed earlier are not feasible directions because it doesn't matter how far you go. It doesn't matter how small the epsilon is. Once you step out, you'll be outside of the omega. So in this case, these 2 directions are not feasible directions. Okay, so this is the intuitive understanding of feasible directions. Okay, so now given the direction, it doesn't matter if it's feasible or not. It's just giving you a concept of you definitely want to do a feasible direction. But let's say that you are given a direction, and the most important concept based on this direction is called directional derivative. Okay, the directional derivative. Okay, so you know no derivative. That's for function f, univariate function f. That means f is from the set of real numbers to the set of real numbers. So that's derivative. What is directional derivative is, recall the picture I drew earlier. So say this is the omega, this is the omega, and this, what I'm drawing are like a level sets. Say this one is decreasing. Say this is a 10. This is a 5. So the directional derivative is that if we're given a point, say I'm given a point here, the direction derivative tells you that if you're given a certain direction, say I'm giving this direction d here, this is my direction, this is x. What is the derivative along that direction? So in this case, you can imagine that although this function, this omega is again in R2, and as I said earlier, the third direction will give you the function value. It will be the f of x direction, right? The direction popping out of the screen, that's the function, the function value direction. Okay, so if you have decided this x, and you have the direction, then you can imagine I'm cutting this line here. Okay, originally you have a function defined on this plane, and which should look like a surface, right? It's floating. You can imagine it's floating on the screen, and you take different values at different point. And if you do this cross section or do this cut, you will cut this surface, and you get a curve. Okay, and this curve can be higher or lower here and there. And what you are trying to do is, what is the derivative there? So, like say in this case, if I cut it here, and then I will get a curve. So let's say just to focus on this line here. I'll plot this line like this one, just laying it down like this one, and then along this line I will have function like this. So now I have this point as my x, and this already tells me direction. So along this one here, along this direction here, I'm laying down here, and the function value is like this. Okay, so if I'm taking a direction like this, then I will have a function value moving like this or moving like this, depending on which direction you go. So if I go this direction, then my function value will be like this. If I going back in this direction, then my function value will go like that. Okay, so in this case, you only have a one-dimensional function because you get a curve here, and the directional derivative is just tells you the derivative at this point. Okay, so in this case, the derivative would be the slope of this tangent line here. Okay, so that's the geometric understanding of our geometrical meaning of directional derivative. Okay, formally what this one is defined is this. So let me explain what this one is. Remember the picture I showed you, the one I just erased? Because since I decided the point, right, and I also decided the direction it goes, so I will have a straight line cutting this omega, and along this line I will have a curve, right? I will have a curve that's showing the function values along this line. Okay, again, as I just mentioned, you just imagine some shape, some kind of surface floating on your screen, between you and the screen, and then that when you do this cut, you get a curved, you will get a curve cross section there, and then this curve gives you a definition of function. So I'm going to define this function like this. I call this function phi of alpha, and what is defined? It is defined as f of x plus alpha d. Here you already decided the x. You determine x and you determine d. The only thing that can change is this alpha. This alpha is a scalar. So to distinguish the vectors and scalars, this x and d, I'm going to label them as vector because x and d are both n-dimensional vectors, right? N-dimensional vector. In the previous example, in the pictures I showed you, x and d are both two-dimensional vectors, because x tells you the location of that point, d tells you the direction. So they are both vectors, but alpha is a scalar. Alpha could be positive or negative. If it's positive, that means you're going from x, you're going along the direction of d. If alpha is negative, then you're going in the negative opposite direction of d. Okay, so alpha can be any real number. So I define this function phi like this way. Then the function phi is a function from R to R. Okay? It takes the value alpha and gives you this f of x plus alpha d. Okay, which is still a scalar. This function is actually the function I draw like this. Okay, this will be alpha. Sorry, I should draw it in this way. When alpha equals to 0, this is when alpha equals to 0. As you can see, when this alpha equals to 0, then this x plus alpha d will be just x. And this is where you start. This is the original point x. Okay, so this is the x. Okay, and that's the when alpha equals 0, you are taking the function value there. When alpha is positive, then you are moving along this direction. Okay, I should draw this. I should switch the left and right. But just give you the idea here that if alpha is increasing, then the function value goes like this. If alpha is decreasing, it's going to negative, then function value like this. Okay, it could be the opposite direction as I drew earlier. It's just that when you fix the direction, you get something like this. Okay, so my point is, since you have this phi defined, this is the phi function, phi alpha. So this is the phi alpha, and the directional derivative of the function f at x with the direction d is essentially the phi prime of 0. Okay, so the directional derivative of f at the point x with direction d is just the phi prime at 0. Okay, the reason is, look at the definition here. So this, according to our definition, is just the phi of alpha. This, according to our definition, is just a phi of 0. Because you take this as 0, then you just have f of x. So the numerator here is nothing but a phi of alpha minus phi of 0. And denominator is alpha. So now I write this as phi of alpha minus phi of 0 divided by alpha. And then I'm taking the limit of alpha for alpha going to 0. And what this is, remember that the phi is just a one-dimensional function. It's phi is from R to R. So this is just the derivative of phi at 0. Okay, and that means the derivative of phi at 0 is this negative number here. Okay, so that is the directional derivative. So what you're really computing is just this quantity here. But formally, how do we really compute this? We don't really go really focus on ourselves onto the phi, although it's equivalent to as doing that. But in practice, how do we compute this directional derivative quickly? So you're given the point, you're given the function f, you're given the point x and the direction d. How do we compute this? Well, if you realize that this directional derivative is nothing but the phi prime at 0, then recall that the phi is like this. So you're going to take the derivative with respect to alpha. And that's just a simple directly taking the derivative because alpha is just scalar. So take the derivative of phi with respect to alpha and then set it to 0. Set alpha to 0. Then that's the derivative, directional derivative of f. So let's do that. So my phi alpha is this. So my phi prime of alpha should be taking the derivative with respect to alpha. But taking the derivative with respect to alpha, here is my alpha. Okay, and it seems I have to use the chain rule. Right? That's the case here. We need to use the chain rule to get to this alpha. So to use the chain rule, we first need to take the derivative of f. But now f is from Rn to R. So the derivative of f is not really called the derivative, it's called the gradient, right? The gradient of f. Gradient f is just the it's just stacking the partial derivatives. It's the f of x1, f of x2, df dxn, right? And you know the partial, what the meaning of partial derivatives. So this is just stacking those partial derivatives, and there should be a n-dimensional vector. Okay, so that's what we're going to get when we take a derivative with respect to f first. So we take a derivative of f, I will get the gradient of f, and I have to keep everything inside unchanged, and then I'll get into the f. So I'm going to use the chain roots. I take the derivative of f first, and then I take the derivative of this thing with respect to alpha. And now inside this is a very simple function of alpha. Give alpha, you give it alpha, then you get a vector. So when you take a derivative with respect to alpha, the only thing that you will get will be just the d, because the d is a constant vector in front of alpha. So that's why when you take the derivative of the inside with respect to alpha, you get just d. So you get the d, and then you're done. You have two. You have the outside gradient of the outside and the gradient of the inside, and you need to make multiply them together. So be careful that what you really got here is this is supposed to be the gradient, so it's a vector. It's an n-dimensional vector. And this d, remember that is also an n-dimensional vector. Okay, and the phi prime on the left-hand side, phi is a function from from R to R. So the phi prime is just a scalar. So on the left-hand side, you should have a scalar here. And how do I get a scalar as a product of two vectors? That's the inner product, right? So you have the inner product of these two vectors, that gives you the R. Okay, so the inner product of the two vectors, you'll know what that is. So you have x1, say you have x1, x2 up to xn. You have y1 through yn. Okay, and taking the inner product of these two, so this dot is the inner product of these two, it will give you x1, y1, x2, y2, all the way to xn, yn. It's just a sum of those component-wise products. Okay, so here you will get a scalar, and that is the directional derivative. Okay, so now just as a summary, to compute the directional derivative, compute the directional derivative, what you need to do is take the gradient of f and evaluate at x, and you get the vector here, and then you have this d as your direction. So if I start from this x and you go along the direction d, then the directional derivative of f at x with the direction d will be just the inner product of the gradient of f at x and the direction d. Okay, so this notation here means that I have a column vector. This has a column vector. This has a column vector. Then when I transpose this column vector, it becomes a row vector. So when I multiply the row vector and this column vector, I can just treat them as matrices, right? So I have row vector, I have a column vector. Then when I multiply them together as matrices, I will just get a scalar. Okay, so that's the directional derivative. So how we use this? So remember the picture I drew earlier. Say this is the value, function value. This circle or this contour tells you the points where the function value is 10. Okay, and then this contour gives you the points where the function value is 5. So now let's say I start from this point, and I decide to go that direction. So this is the x, this is direction d, and by evaluating the directional derivative, I can tell that if I'm going down or going up. Right? If this directional derivative is a negative number, that means I'm going down along the direction d. If it's a positive number, that means if I go along the direction d, I will increase my function value. At least locally, near x, I'm going to get a larger function value. So this is the word we're going to use this later. Okay, but right now you just need to know what this directional derivative is and how do we compute it. Okay, so now let's give an example. Okay, suppose I have a function f that's R3 to R. So my function is given like this. It's for any x, a three-dimensional vector x, it has three components, x1, x2, x3. Then the function value is x1 times x2 times x3, which is a scalar. Okay, and now we're given this point, this direction, and the question is, what is the directional derivative of f at any point x with this direction? So the x is undetermined. X is just any point x is having this x1, x2, x3 as components, and we're trying to figure out what's the directional derivative. So let's say this is the f, right? And we first need to form the gradient. The gradient of f should be the partial derivative of f with respect to x1, partial derivative of f with respect to x2, and partial derivative of f with respect to x3. That's the vector. So for this function, for the first one, we're going to fix x2, x3 as constants. Just take the derivative with respect to x1. So as you can see, when I take the derivative with respect to x1 with x2 and x3 fixed, then the derivative will be just x2, x3. Right? So they will be just x2, x3. And then partial derivative with respect to x2, then we have just x1, x3. And the partial derivative with respect to x3 will be x1, x2. Okay, this is my gradient. And as we showed earlier, the directional derivative of f at x will be just the inner product of the gradient and the directional derivative, the direction. So the gradient is this, the derivative is this. So to just take inner product of them. So that's what I'm drawing here. So this is the gradient, which is when I take the transpose, it will be a row vector. And the d is this. I put this t here just means it's transpose. So now what you need to do is make the inner product. So you multiply this and this, plus this and the product of this, plus the product of this two. Okay, and eventually you will get this as a directional derivative. And remember that this is a scalar. Okay, so we have talking about some basic concepts of directional derivative, and now we're going to ask, suppose we're given this function f, and how do we characterize the minimizers? Right, what kind of conditions the minimizers should satisfy? Okay, so now we're going to give the first order necessary condition. We're going to talk about this in much more details later, but you need to have a rough understanding or intuitive understanding what this first order necessary condition is. So this actually goes back to the one-dimensional case. Suppose I have a one-dimensional function like that. You all know that we're trying to find a minimizer. You should first find the critical points, which are the points having derivative equal to 0. Okay, and that is the case there, right? These points have derivative equal to 0. So if it is minimizer, then at least it has to have derivative equal to 0. This is only for the case where function f is differentiable, and also we're dealing with unconstrained case. If it's constrained, then not necessary equal to 0. For example, you have a constraint. Say I need to constrain my function of my point x into this interval, and now I have this function, say like this. Okay, but my minimizer can be only taken over this interval, which I call omega. And now you can see that the minimizer will be this point, this right end point. but there the derivative is not 0. So when you have a constraint, then the critical point is not necessarily giving you, or the minimizer is not necessarily critical point. But if it's unconstrained and the function f is differentiable, then a minimizer, a local minimizer, or global minimizer, they must be critical points. Okay, so these are necessary conditions for a point to be a local minimizer, but it's only for the unconstrained case where f is differentiable. Okay, so let's just focus on this case for right now. So the f is differentiable. The first order necessary condition says that if x star is the local minimizer, then for any feasible direction d at x star, there is this. Okay, so it looks a little bit complicated, but it's actually very, very intuitive. Let me show you why this, what this one is. So first of all, at the left-hand side, this is the, as we showed earlier, this is just the directional derivative of f at x star along direction d. So x is the local minimizer, then this is greater than 0 means that any directional derivative, the directional derivative along any feasible direction is greater than or equal to 0. Okay, so let's first think about the unconstrained case, or x is actually a point inside omega. Say this is the x star, and I'm having these contours. Let's say this is really the minimizer. This is really the minimizer here. Okay, if it is a minimizer, then that means if you go along any direction, your function value should not increase, should not further decrease. Because if you go along a certain direction and the function value further decreases, that means x star is not a local minimizer, right? So if x star is local minimizer, then that means any directional derivative should be greater than or equal to 0. And that is exactly the meaning here. This is the directional derivative. The d is any of those 5 directions, any of those directions actually. The inner product is greater than or equal to 0. So it means the directional derivative is going to be non-negative or greater than or equal to 0. That means go along the direction d, the function value cannot decrease. It's always trying to stay constant or increase. Okay, that's the case here. If you go along any of those directions, the function value will not decrease. It's greater than or equal to 0. So as you can see, this is this, if x star is local minimizer, then this has to be true, right? This is for the point x as a to be a low interior point of this omega. If x happens to be on the boundary, say this is a let me see this. So this is the omega, and you actually have this point x star as a local minimizer. All the other points are actually having function value larger. Okay, and then in this case, you don't really care what happens when the direction is not feasible. You only care what happens when the function direction is feasible. Like in this direction, this directions. So if x star is a local minimizer, like in this case, then you go along any feasible direction, your function value should not decrease, and that means the directional derivative will be greater than or equal to 0. Okay, so that is this is also tells us this case here. So this is a directional. This is not a feasible direction, right? So it doesn't count. Only care this direction, which is feasible. At this point, only you go left. That is a feasible direction. And as you can see, go along this direction, the function value, the derivative is increasing. The derivative is positive, and that's increasing. So this is the local minimizer. Okay, so if in high-dimensional case, then you have this. Okay, you can see the difference between this one and this one. If x is on the boundary, then you only care about the feasible directions. But if x is the interior point, then all the directions are feasible, right? Because you can go any direction. And if this one is true for any direction d, if this one is true for any direction d, that just means this gradient equals to 0. Okay, and that is what I'm going to say next. If x is the interior point, then the first order necessary condition will be just gradient f equals 0. And that is the case here. So if you have these points x as interior points, where maybe this is the original omega, or maybe the entire line is omega, but these points are interior points. And in this case, the for a point to be a local minimizer, then the derivative has to be 0 there. Okay. So let's take a concrete example and check a local minimizer, the first order necessary condition for this. So we have a function f, and it's a function of Rx, and x has two variables, x1, x2. So it's defined in this way. And we are going to have a constraint here. The omega has to be x1 to satisfy this. So that means you have this part as your omega. Okay, your minimizer has to be from the first quadrant. This is x1, this is x2. The function value is, again, is pop up the screen. It's the f, the third direction, gives you the value of fx. Okay, the first question is, if this first order necessary condition is satisfied at this x equals to 1, 3. So say this is the one, let me erase this shades. So remember that the whole first quadrant is omega. So it's x1, it's x2. So apparently this point here is the interior point. So that means any direction is a feasible direction. So if I want to see if I want to see whether the first order necessary condition is satisfied there, I just need to check if the gradient is 0 there, right? Because that's the second case we talk about here. If it's the interior point, then the first order necessary condition is just that gradient f is 0 there. So let's check. So to do that, we first compute the gradient. The gradient of f, we said it would be just the partial derivatives. So the partial derivative with respect to x1. So the first component is the partial derivative with respect to x1. And let's say that in this case, we're going to fix x2 as a constant, and only take a derivative with respect to x1. That gives us this, right? And when we take a derivative with respect to x2, we'll have this 0.5 times 2 times x2, which gives me x2 plus 3. So this is the partial derivative. This is the gradient of f. Okay, this is the gradient of f, and that's how we got this. Okay, I showed the answer here. And let's check. In the first case, if it's a local minimizer, if this point is local minimizer, since it's the interior point, the local the first order necessary condition is just to check the gradient of f at this point. So we just need to plug in x1 equals to 3, x1 equals to 1, x2 equals to 3 into this. So if you plug in, you can see that it's definitely not 0, right? So it's not 0, that means this x cannot be a local minimizer, because the first order necessary condition is failed there. Okay, so that's the first. Second, you check the local the first order necessary condition for this point. So this point is 0, 3. 0, 3, that means it's here. It's right here, and that is on the boundary, right? That's on the boundary, because the point, the omega, is actually the first quadrant. So I need to first compute the gradient at this point, and I'm going to plug in x1 equals to 0, x2 equals to 3. So I've got 0, 6. And now the d is not arbitrary. The feasible directions, you look at this picture here, what are the feasible directions? You can go any of those directions. You can go this direction, this direction, this direction, this direction, any of those directions, as long as you're not going this direction. Okay, so all those are possible. All those are feasible directions, and let me characterize what are the feasible directions. Should be the set of directions. Say the D is D1, D2, where since you can only go this kind of directions, so the x1, the D1 has to be greater than or equal to 0. D2 can be any direction, right? D1 has to be, non-negative, but D2 can be any direction, right? Either this direction or this direction. So this will be just D1 greater than or equal to 0, and D2 can be any real number. Okay, now you check the if you have any feasible direction D, and you multiply it, you take an inner product with this gradient f, and the gradient f of x times D, the inner product of D, will be just equal to 0, 6 times D1, D2, and that will be just 6 times D2. And let's see if it's always greater than or equal to 0. And apparently it's not, right? Because this D2 can be negative, so 6 times D2 could be negative. So the first order necessary condition is again failed at this point. Okay, and similarly you can do the others. Say the third one, the x is 1, 0, so it's here. Okay, so the gradient f, I'll just give you the result. You just plug in x1 equals to 1 and x2 equals to 0. You have 2 and 3. Right? And the feasible direction will be just the D. Again, it has 2 components, and now you can see this kind of directions, right? So the D1 can be any direction, can be any number, but D2 has to be non-negative. So you have D1 is a real number, but D2 has to be greater than or equal to 0. And now when you multiply the 2, you have 2, 3 times D1, D2, and that is equal to 2D1 plus 3D2. Apparently, we cannot guarantee this to be non-negative, right? You can choose, for example, you can choose D2 to be 0 and D1 to be -1, then you get negative number here. So it's not the first order necessary condition is not satisfied there. Okay, similarly, we can do the last one where x is 0, 0. So this is the x. When I take the gradient f, at this point, I'll have to plug in 0, 0 there. So it will be 0 and 3. The feasible direction. So in this case, the feasible directions are more special. Can be only these directions. So the D1, D2 must be both non-negative, right? So the D feasible directions will be the collection of vectors where D1, D2 are both non-negative. So when I take the gradient of this 0, 3 and this D1, D2, I'll get 3D2. But D2 has to be non-negative, so this has to be non-negative. Okay, finally we have this point x, the point 0, 0, and at this point the first order necessary condition is satisfied. Okay, so that's the first order necessary condition, and we can also talk about the second order necessary condition, and this is just to eliminate those this kind of points. Let me show. Okay, as we showed earlier, this point, this point, this point, this point, they all have derivative equal to 0. But apparently, this will be a local minimizer, this will be a local minimizer, but these two are not. Okay, so how do I get rid of these 2 points? That's the second order necessary condition. Okay, let's check what that is. The second order necessary condition, if x is a local minimizer, then for any feasible direction d at x star with this equal to 0, so that's so that means go along that direction, the function value is going to the derivative is flat there. The derivative is 0 and the tangent line is flat there. In this case, if this is greater than 0, then this is second order. So this is the second order necessary condition. If x is a local minimizer and along any direction d that you have this, then does d satisfy this. This is the second order necessary condition. Okay, so what that means is going along that direction, let me recall you that the function we had earlier. For the function phi, alpha, I defined it to be f of x plus alpha d. Okay, and then we said that the phi prime of 0 is the directional derivative of f. Directional derivative of f at the point x along the direction d. If x is the local minimizer, then the directional derivative must be non-negative, right? And you want to avoid case like this. You want to avoid this kind of cases. Then what that means is, if you have this phi of alpha, and then you try to take a Taylor expansion of this phi. So it will be phi of 0 plus phi prime of 0 times alpha plus 1/2 phi double prime at 0 and alpha square. And all the other things are alpha cube, which means they're much smaller. Okay. So let's translate this into the original function there. So the phi alpha becomes f of x plus alpha d. This is just the f of x. This is alpha times the directional derivative, which is gradient f at x times d, right? And this one here, so if I take the second order derivative, if I take the first order derivative, that gives me gradient f x plus alpha d times d. If I take the second order derivative, or take a derivative of with respect to alpha again, then I'm going to do the chain rule one more time. And if I do the chain rule, I'll need to take a derivative of the gradient f. That gives me the Hessian, okay, the Hessian matrix. And then when I take the derivative of inside, so I take the derivative of this. First, I need to take the derivative of that, and that's giving me Hessian. And take the derivative with respect to alpha here, and I'll get another d. So in total, what I'll get here is actually the d vector transpose times the Hessian of f at x plus alpha d, and the d. Okay, so this is a row vector here. This is a Hessian is a matrix here, and D is this. So when you multiply this row vector, matrix, and column vector, I will get scalar. So this is the F double prime. When you evaluate the alpha equal to 0, then it just means phi double prime of 0 will be just a D transposition of F at X and then another D. Okay, so this value here is just 1/2 D transposition F X D times alpha squared. Okay, so if at the point X going along the direction D, the function value will be this one or this one here. Okay, so this will be the function value, and it can be written as a sum of this, this, this. And this one will be very small, so we don't really care about that. So this is the function value at the point original X. So it's the function value here. And going along that direction, if this is equal to 0, so it means this part is 0, then since X, you want to check if X star is local minimizer or if it is local minimizer, then going along this direction, this function value should be increasing, right? Because this will be the minimizer. This is the point you moved to. So this value should be bigger than or equal to this. If this is bigger than or equal to this, at this point we have shown that this is equal to this one here is equal to this, and this small number there. Well, this is already 0, as we said, because this. And you want this left-hand side to be greater than this. Then the only thing that I can do is to make sure this is greater than or equal to 0. And this is the D Haitian D. Okay, so that's the one here. That's the second order necessary condition. Okay, so if X star is local minimizer, then along any feasible directions such that the directional derivative is 0, then you should have this. You should have this quantity here. So for any feasible directions such that this holds, you should have this. And that's the geometric meaning there. Sorry, not geometric meaning. We do the Taylor expansion. That's why we require this to be greater than or equal to 0. Okay, if it's interior point, if X is the interior point, then you know that this is anyway 0 because the gradient F will be 0. So if X is interior point, then this should be 0, and then this is automatically satisfied. So this is always 0. And you want this to be, if X star is local minimizer, the second order derivative, let's go back to check this. This D can be any number, any vector. If this is true for any direction D, if this is greater than or equal to 0 for any direction D, that just means this matrix is positive semi-definite, right? Remember the definition for matrix to be positive semi-definite. So I have a matrix M is positive semi-definite. That means for any X, the X transpose MX. So X is when I write a vector, we also assume it's a column vector. So in this case, you have row vector, square, and column vector. If this is always greater than 0 for any X, then we call this positive semi-definite. Okay. So by the way, what is a positive definite? Positive definite means that this is greater than for any X non-zero. This is greater than or equal to 0. Well, if X is 0, then apparently no matter what, this quantity will be always 0. So, but if for X non-zero, this must be positive, then we call this positive definite. Okay. For positive semi-definite, you could have some non-zero X such that this is still 0. Okay, that's for positive semi-definite. That is the notation here. When I write this, that just means the function, the matrix there is positive semi-definite. Okay, so if this is true for any D, then that just means this is positive semi-definite. Okay, and that's the notation here. Okay, remember that these conditions are all necessary but not sufficient. Oh, by the way, how we get back to this? So why this can help us to eliminate this, these two cases? Remember that this is a Hessian. That's for vector value variables. So the x is a vector. But if x is just a scalar, then this Hessian is just a second order derivative. So what this requires is that the second order derivative of f should be greater than or equal to 0. And now you can see that at this point right here, and this point, the second order derivative is positive because these are concave functions. So at there, the second order derivatives are negative. At these 2 points, the second order derivative are positive. Okay, so if you check the second order necessary condition, you get rid of these 2 points because their second order derivative are negative. Okay, finally, let's say check that the original conditions are only necessary but not sufficient. Okay, so if x is the local minimizer, then must satisfy those. But if you have those conditions, they do not guarantee that the x star is a local minimizer. Okay, let's see an example here. So I have a function f defined as x cubed. Then you can check the derivative of f will be 3 times x squared, right? So the f prime will be 3x squared. F double prime will be 6x. Okay, so you check the first order necessary condition. At 0, you see plug in 0 here, and you just get 0. If you plug in 0 into the second order derivative, you also get 0. So they do satisfy the first order and second order necessary conditions, but it's not a local minimizer. If you look at the picture of the x cube, it's the x cube looks like this. So this is the x cube. So here you do have derivative equals 0. The tangent line is actually slope is a 0, is a flat there. The tangent line has a derivative 0 there, but it's not local minimizer. Okay, you can move left or right. If you move to left, the function value will decrease. Okay, let's look at another example. I have function f defined as 1 squared minus x2 squared, and the gradient is this. Okay, and then you take the Hessian. The Hessian will be just the collection of the second order derivatives. So this will be df dx1 squared, right? The Hessian of f will be df dx1 squared, df dx1 dx2 dx2 dx1 dx2 squared. But if the function is if the function has second order derivative, then these two should be equal, as you know in calculus. Okay, so let's go back to this example. You have this as your f, and then this is gradient. The second order derivative will give you the second order partial derivatives will give you this Hessian matrix, which is this. Okay, and you can see this matrix is not positive semi-definite. The reason is if I multiply some x1, x2 on the left and x1, x2 on the right, and I will have 2x1 squared minus 2x2 squares. So it's not always greater than or equal to 0. Right? So this matrix is not positive semi-definite. So now let's check that if we take the gradient, you set this to 0, and you do have x1 and x2 equals 0, and this satisfies the first order necessary condition. But when you check the second order necessary condition, then you get this matrix has a Hessian matrix, and it's not a positive semi-definite, so it does not satisfy the second order necessary condition. And from this you can conclude that although you can set this theorem to solve for the local critical point, but this critical point, which is 0, 0, is not really a local minimizer. Okay, so what would be the sufficient condition for a local minimizer? So at this point, let's just consider the case where the local minimizer you found is an interior point. So by that, what I mean is that you have this as 0 omega, and you found this x star, and you're trying to see if it's a local, really a local minimizer. So if it's a local minimizer, at least in this case, the gradient has to be 0, right? That's what we showed. For a point to be a local minimizer, an interior point to be a local minimizer, the gradient has to be 0 there. You always assume that f is differentiable throughout, so the gradient does make sense. Does make sense. So the gradient has to be 0. But how do we guarantee that it's actually a local minimizer? If you have this additional condition here, if the Hessian is positive definite, then this point x here will be a strict local minimizer. Okay, so this is a second order sufficient condition. So you have the gradient equal to 0. If I have x as the interior point, the gradient is equal to 0, and the second order derivative of the Hessian is positive definite. Remember what we defined it earlier. If it's a positive definite, then this x is a strict local minimizer. Okay, so at this point, we have talked about several different scenarios to characterize a local minimizer. So as I said earlier, we are given a optimization problem. Usually is presented as a minimization problem. We have the objective function, we have the constraint omega, and usually we can only find local minimizers. But how do we characterize it? How do we know that this x we found is a local minimizer? We have first order and second order necessary conditions. This will tell us that if a point is possible to be a local minimizer. So if it's local minimizer, it has to satisfy those. Okay, and we distinguish this into two different cases. If x is an interior point, that's very simple. The first order necessary condition is just that gradient is equal to 0. If the x is not the interior point, it's on the boundary, then it is a little bit complicated. The first order necessary condition tells us that along any possible feasible direction, the gradient, the directional derivative should be non-negative. And then we move on to the second order necessary condition. That means that's the one we showed earlier. Here, right? And then we move on to the second order sufficient condition. In this case, we only talk about the x as a interior point. In this case, this is a sufficient condition for x to be a local minimizer. Okay, this corresponds to the case earlier, like this, and this one, these 2 points, their second order derivative is strictly positive. So it's like the Hessian is positive definite. And in this case, those 2 points are strict local minimizers. Okay, let's take an example for the second order as a sufficient condition. If you have f defined as x1 squared, x2 squared, then the gradient is this, then the Hessian matrix is this, and if it's set this to 0, you get x1, x2 both as 0. So 0, 0 is a point satisfying the first order necessary condition, and then you check this. This is a Hessian. That is the Hessian at all the points. All the points have the same Hessian here. And then you can see this is a positive definite matrix because we multiply x1, x2 on the left and another x1, x2 On the right, you just have 2x1 squared plus 2x2 squared, which is always greater than 0 for non-zero x1, x2. Right? So this is positive definite matrix. So according to the second order sufficient condition, 0, 0 is actually a strict local minimizer.